Our planets are not fixed in their orbits. They have traveled vast cosmic distances from where they were born. This is planetary migration, the solar system's greatest unsolved mystery. By the end of this story, you will understand the violent events that forged our cosmic home from chaos. We will uncover why Mars is so small, what scarred the face of the Moon, and whether a hidden giant planet still lurks in the dark. The quiet order we see today is a lie covering a past of gravitational pinball and wandering worlds. What does a stable home in the universe truly cost? The cost was a violent rearrangement of our entire neighborhood. To understand this, we must first grasp the central idea: planetary migration. It is a simple yet radical concept. Planets can move. They are not born in their current orbits and then stay there forever. Instead, after a world forms from the dust and gas of a young star, it can embark on a grand journey, shifting its position by millions, even billions of miles. This changes everything. For centuries, we viewed our solar system as a static clockwork, a perfect, unchanging mechanism set in motion long ago. The planets we see today were thought to have always been right where they are, tracing the same elegant loops around the sun. That view is wrong. Our solar system is dynamic, a system that has lived a dramatic life, sculpted by wandering giants and gravitational chaos. The quiet orbits we see now are merely the calm after a cosmic storm. So how does a planet, an object of immense mass, actually migrate? It does not have engines. It does not propel itself. Instead, it is pushed and pulled by the very fabric of its young solar system. One of the most powerful forces for early migration is the protoplanetary disk, that vast, swirling pancake of gas and dust from which planets are born. A young planet, as it orbits, creates waves in this dense gas. Think of it not as a rock floating in empty space, but as a heavy stone dragged through a thick, syrupy fluid. The interaction between the planet and these waves creates a tug of war. Usually, the planet loses orbital energy, causing it to spiral inward, slowly surfing the gas disk toward the central star. It is a cosmic surfer riding a wave of its own making toward a dangerous shore. But migration is not just about a planet and a disk. It is also about planets interacting with each other. When two or more young giants share a solar system, their immense gravitational fields act like invisible ropes pulling on one another. This can lead to a gravitational dance so unstable it resembles a game of cosmic pinball. A gentle nudge can become a shove. A close encounter can fling a world into a wildly different orbit, sending it careening inward toward the heat or outward into the freezing dark. This is the heart of the mystery. Migration is the force that can take a calm, orderly nursery of infant worlds and turn it into a battlefield where orbits are prizes to be won or lost through sheer gravitational might. The solar system's violent adolescence finally has a name. It is called the Nice Model, named not for being pleasant, but for the city in France where astronomers first pieced this revolutionary story together. For decades, the standard view was one of quiet, gentle growth. Planets formed in placid orbits and stayed there, a peaceful family from the very beginning. The Nice Model shattered that illusion. It proposed something radical and thrilling. In the beginning, the giant planets Jupiter, Saturn, Uranus, and Neptune did not live in their current distant orbits. They were huddled together, a tight-knit group much closer to the Sun and to each other. Picture them not as the far-flung monarchs they are today, but as siblings in a crowded nursery, orbiting within a region of space no wider than the current distance from the Sun to Uranus. This compact configuration was stable, but only for a while. It was a calm before a storm of unimaginable scale. The stage was set not just by the planets themselves, but by the leftovers of planetary construction, a vast sea of icy planetesimals, the frozen building blocks of worlds swirling in a disk beyond the giants. This crowded, dynamic system was a ticking clock. Gravity is a patient sculptor, and in that dense environment, subtle tugs between the planets and this sea of debris were slowly adding up, storing energy like a coiled spring. The nice model gave us the blueprint for the chaos. It explained how our solar system could have evolved from that tight, compact beginning into the spacious arrangement we see today. It provided the why behind the Great Migration, the mechanism for the pinball game. This was not a random, violent free-for-all, but a structured, almost inevitable sequence of events triggered by the planet's own gravitational influence on their environment. The model appended everything we thought we knew about planetary stability, revealing that our home system's peace was hard-won, the result of a catastrophic reshuffling that forever altered the fates of every world within it. That crowded nursery could not last forever. The trigger for its explosive rearrangement was a delicate and powerful cosmic alignment, a gravitational tango between the two largest giants, Jupiter and Saturn. For millions of years, they orbited the Sun in that compact space, their path slowly, imperceptibly changing under the gentle but persistent pull of the surrounding sea of icy debris. This relentless nudging altered their orbits, shifting them millimeter by cosmic millimeter until they crossed a critical threshold. Their orbital periods, the time it takes to complete one loop around the Sun, fell into a precise mathematical lockstep. Jupiter completed 2 orbits for every 1 orbit of Saturn. This is called a 2-to-1 mean motion resonance. It sounds like a harmless bit of celestial clockwork, but in reality, it is one of the most powerful destabilizing forces in planetary dynamics. Think of it not as harmony, but as a perfectly timed push on a swing. If you push a child on a swing randomly, the motion stays small. But if you push at the exact right moment in each arc at the point of peak momentum, you add a little energy every time. The swings grow higher and higher, amplifying the motion until it becomes wild and uncontrollable. That is what the resonance did. Every time Saturn caught up to Jupiter in their cosmic lap at that same precise orbital position, Jupiter's gravity gave it a synchronized gravitational shove. These periodic, perfectly timed kicks did not cancel out. They stacked, they amplified. The resonance acted as a gravitational lever, prying the 2 giants apart and injecting a massive dose of chaos into the entire system. The stable, compact configuration of the 4 planets was suddenly and violently unstable. The quiet gravitational nudges from the past were now a roaring engine of change. The solar system's clockwork had found its breaking point, and with that resonant lock, the Great Migration began in earnest, unleashing forces that would scatter worlds and reshape our cosmic neighborhood forever. The resonance was the spark that ignited the powder keg. With Jupiter and Saturn now locked in their amplifying dance, the entire delicate balance of the inner solar system collapsed. The 2 giants began to violently repel each other, their orbits stretching and warping. This created a gravitational tsunami that crashed over their smaller siblings, Uranus and Neptune. In a breathtakingly short span of time, perhaps just a few hundred years, the orderly nursery erupted into chaos. Uranus and Neptune were caught in the crossfire, flung from their cozy orbits like stones from a sling. They were sent careening outward directly into the vast, pristine disk of icy planetesimals that lay beyond. This was not a gentle drift into open space. It was a catastrophic plunge into a cosmic shooting gallery. Imagine a giant bulldozer plowing into a field of frozen boulders. That is essentially what happened. As Uranus and Neptune plowed through this dense sea of primordial ice, their immense gravity scattered the smaller bodies in all directions. Some were hurled inward toward the Sun, becoming comets. Others were ejected entirely, cast out into the interstellar void to wander forever as rogue planets. But with every action comes an equal and opposite reaction. For every icy planetesimal that Neptune flung away, Neptune itself received a tiny gravitational kick backward like the recoil from a gun. This process, called gravitational scattering, acted as a relentless engine. Each close encounter with a frozen world pushed the giant planets a little farther out. Neptune, in particular, underwent a staggering migration. It may have started its life closer to the Sun than Uranus, only to be catapulted past its sibling in this gravitational free-for-all, ultimately claiming the outermost orbit we see today. Meanwhile, Jupiter, the most massive of them all, did not escape unscathed. Conservation of momentum dictated that as the other giants moved outward, something had to move inward. Jupiter became that counterweight. It executed a small but crucial inward march, tightening its orbit around the Sun. This slight shift by the solar system's gravitational kingpin would have profound and devastating consequences for the smaller, rocky worlds huddled closer to the Sun's warmth. The solar system was being remade in fire and ice, and the tremors of this giant planet scramble were about to reach the fragile inner worlds. The proof of this ancient upheaval is written in the sky itself, etched into the very paths the planets follow. The current orbits of Jupiter, Saturn, Uranus, and Neptune are not random. They are the fossilized record of that long-ago migration, a cosmic crime scene where gravity left its fingerprints. Consider their spacings. The giant planets are not evenly distributed. There are vast, seemingly empty gaps between them, especially beyond Jupiter. If they had formed peacefully in place, we might expect a more regular stair-step arrangement. Instead, we see the aftermath of a scattering where planets were flung outward to their present positions by violent gravitational interactions. Their orbits also tell a story of past violence. Each planet travels around the Sun not in a perfect circle, but in a slightly squashed ellipse, what astronomers call orbital eccentricity. They are also tilted at slight angles relative to the Sun's equator, known as orbital inclination. A calm, gentle birth should have left these worlds on nearly circular, flat orbits. The eccentricities and inclinations we observe today are small, but they are significant. They are the lingering wobbles from that great gravitational shake-up, the subtle tremors that remain after the earthquake has passed. The most compelling evidence, however, lies far beyond Neptune in the deep freeze of the outer solar system. The structure of the Kuiper Belt, that distant realm of icy bodies, is the ultimate witness. This belt is not a smooth, featureless donut of debris. It is sharply sculpted with distinct populations of objects clustered at specific orbital distances. Some of these groupings, like the Plutinos that share an orbital resonance with Neptune, make no sense if the giant planets have always been where they are now. Their existence is a direct prediction of the Nice model. They are the stranded remnants of that primordial disk, captured and shepherded into their peculiar orbits during Neptune's grand outward migration. The architecture of our entire planetary system, from the spacing of the giants to the frozen patterns in the Kuiper Belt, points to one inescapable conclusion. Our solar system is a survivor of a violent past, and its current order is the beautiful, quiet scar tissue left behind. The tremors from that outer solar system scramble did not stay confined to the realm of the giants. They rippled inward, a wave of gravitational chaos that reached the fragile construction zone where the rocky planets were taking shape. This is where the story turns from a tale of wandering giants to one of direct, catastrophic consequence for worlds like our own. The primary victim of this inward shockwave was the asteroid belt. Today, it is a sparsely populated ring of rubble between Mars and Jupiter, often depicted in movies as a dense, impassable field of tumbling rocks. In reality, it is mostly empty space. If you were to stand on an asteroid, your nearest neighbor would likely be hundreds of thousands of miles away. The total mass of the entire belt is less than that of our moon. This emptiness is the first major clue. It tells us the belt was not always this barren. In the solar system's youth, this region was far richer, a dense disk of planetesimals, the building blocks of a planet that never was. So what happened to all that material? The answer lies in the Great Migration. As Jupiter performed its crucial inward jump, driven by the resonance with Saturn, it moved perilously close to this fertile belt. The gravitational influence of the solar system's largest planet is immense. Think of it as a cosmic wrecking ball swinging through a delicate structure. Jupiter's migrating gravity would have stirred the primordial asteroid belt like a spoon in a soup, injecting tremendous orbital energy into the millions of small bodies there. Most of them did not survive the onslaught. They were violently scattered, their fate sealed by Jupiter's passing fury. A vast majority were ejected entirely from the inner solar system, flung into the outer darkness or on sun-grazing paths that led to their destruction. A significant fraction, however, were thrown inward toward the sun, on collision courses with the still-forming terrestrial planets Mars, Earth, Venus, and Mercury. This epic scattering event explains the asteroid belt's present-day poverty. It is not a failed planet, but a surviving remnant, the devastated ruins of a once thriving region that was cleared out by a passing giant. The event also explains the belt's puzzling composition. We find a bizarre mix of objects there, not just dry, rocky asteroids, but also bodies rich in water and organic materials, more akin to the icy planetesimals of the outer solar system. How did ice survive in the warm region between Mars and Jupiter? The migration provides the delivery service. As Uranus and Neptune plowed through the outer disk, they would have hurled a rain of primitive, icy material inward. Some of these frozen wanderers were captured and stranded in the asteroid belt during the gravitational turmoil, becoming the water-rich asteroids we see today. This grand reshuffling did more than just sculpt the belt, however. It set the timer for a period of unimaginable violence in the inner solar system, a celestial storm whose scars we can still see on worlds next door. This inward rain of cosmic debris was not a brief shower. It became a cataclysm known as the Late Heavy Bombardment, a period of intense violence that reshaped the surfaces of every rocky world. For hundreds of millions of years, starting around 4 billion years ago, the inner solar system was a shooting gallery. Asteroids and comets slammed into the young planets with terrifying frequency, carving out vast basins and melting entire landscapes. The face of our moon, with its countless craters and dark, smooth maria, is the most pristine record of this ancient pummeling we have. For decades, this bombardment seemed like a random, inevitable phase of planetary construction, the messy cleanup after planet formation. But the timing was always a puzzle. Why would this intense barrage begin so late, hundreds of millions of years after the planets themselves had mostly formed? The NICE model provided a stunning and elegant answer. The late heavy bombardment was not a random event. It was a direct consequence, a delayed echo of the great planetary migration happening far away. The clockworks align with chilling precision. According to the model, the resonant dance between Jupiter and Saturn and the subsequent scattering of Uranus and Neptune would have occurred at roughly the same time the geological record shows the bombardment began. This is not a coincidence, it is cause and effect. As the giant planets rearranged themselves, they acted like gravitational catapults. The primordial sea of icy planetesimals from the outer disk and the rocky debris from the ravaged asteroid belt were suddenly and violently stirred. Countless chunks of rock and ice were flung sunward, their new trajectories crossing the orbits of Mars, Earth, Venus, and Mercury. The previously calm inner system was inundated by projectiles from a distant war. The late heavy bombardment, therefore, is the forensic evidence linking planetary migration directly to our own world's history. Those ancient impacts delivered more than just destruction. They likely brought water and the organic compounds necessary for life, seeding the early Earth with the very ingredients of our existence. The same event that scarred the moon may have also filled our oceans. This transforms the narrative completely. The violent migration of the giant planets was not just a distant rearrangement of frozen worlds. It was an event that reached into the heart of the solar system, hammering the terrestrial planets and perhaps even setting the stage for life itself on one of them. The quiet order we inherited was forged in a storm of collisions, a storm triggered by wandering giants. Our own moon is a silent witness to this ancient bombardment. Its pale, cratered face, a familiar sight in our night sky, is not just a collection of random pits. It is a detailed historical record, a celestial diary etched in stone. The dark, smooth patches we call the Maria, Latin for seas, are the most dramatic entries in that diary. These are not oceans, but vast plains of solidified lava, basalt that welled up from the moon's interior to fill the deepest wounds. Each mare is the scar from a cataclysmic impact, a blow so powerful it cracked the lunar crust and allowed the molten mantle below to flood the basin. The impact that created the Imbrium Basin, for example, one of the largest Maria, was an event of almost incomprehensible violence, likely caused by an asteroid the size of a small country. The lava that filled it later is a testament to the sheer depth of the trauma. But the true evidence for a sudden, concentrated storm of impacts lies not just in the existence of these giant basins, but in their age. By analyzing lunar rocks brought back by the Apollo missions and studying the crater counts across different regions, scientists can date these events. The story told by the rocks is startlingly clear. While the moon formed around 4.5 billion years ago, the vast majority of the large Maria and the craters that blanket the highlands were formed in a relatively narrow window of time. The ages cluster tightly around 3.9 billion years ago. This is not a pattern of steady, random pummeling over billions of years. It is the signature of a spike, a cataclysm. The lunar surface froze this moment in time, preserving the evidence of a solar system suddenly and violently filled with projectiles. Look up at the full moon. The stark contrast between the bright, rugged highlands and the dark, smooth Maria is a direct visualization of this ancient disaster. The highlands are the original, ancient crust, absolutely saturated with craters from that period. The Maria are the healing scars, the lava that sealed the deepest gashes. This is not a quiet history. It is a story written in fire and rock, telling us that after a long period of relative calm following the moon's formation, something terrifying happened. That something was the gravitational shockwave from the Great Migration, turning the inner solar system into a cosmic battlefield and leaving our nearest celestial neighbor permanently scarred as its most enduring monument. Mars presents a silent but profound mystery, a puzzle written in its very size. Orbiting just beyond Earth, it is a world only half our planet's diameter and a mere tenth of its mass. According to every standard model of how solar systems form, this makes no sense. In the primordial disk of dust and gas around the young sun, the region where Mars was built should have been rich with material. There should have been enough rocky building blocks to form a planet at least as large as Earth, if not larger. Yet Mars is a runt, a small, dry world that seems to have starved in the midst of a cosmic feast. This is the small Mars problem, and for decades it has been one of the most stubborn riddles in planetary science. Why is our neighbor so disappointingly tiny? The answer may once again lie in the chaos of the Great Migration, specifically in the fateful inward jump of Jupiter. Picture the infant solar system before the giants began to move. The region that would become the asteroid belt was a dense, fertile zone of planetesimals, rocky chunks ranging in size from mountains to small moons. Mars was forming just inside this region, greedily accreting material, growing steadily. But then the resonance between Jupiter and Saturn was triggered. As Jupiter shifted slightly inward toward the Sun, it did not move into empty space. It skirted the inner edge of that primordial asteroid belt, its gravity acting like a massive, disruptive force. The effect would have been catastrophic for Mars's future. Jupiter's immense gravitational pull would have stirred the material in that zone with tremendous violence. It injected orbital energy into countless planetesimals, sending them on wild, eccentric paths. Many were flung completely out of the solar system. Many more were thrown sunward to be absorbed by the growing Earth and Venus. But for Mars, orbiting in the crossfire, the result was a sudden and severe famine. The very building blocks it needed to grow to full size were scattered, stolen away by the passing giant. Mars was left stranded in an orbit that had been gravitationally cleaned out, a world frozen in its adolescence, forever stunted. This idea transforms Jupiter from a distant king into an active participant in the story of the rocky planets. Its migration was not a harmless shift in position. It was an act of cosmic theft, robbing Mars of its destiny. The small red planet we see today, with its thin atmosphere and silent, barren plains, may be the direct consequence of Jupiter's ancient journey. Its small size is not a quirk of birth, but a scar from a gravitational upheaval, a permanent record of the day the solar system's largest world decided to take a step closer to home. But Jupiter's migration might have been even more dramatic than a simple inward step. There is a compelling and elegant idea that the king of planets performed a cosmic U-turn, a maneuver so bold it is called the Grand Tack. Picture the early solar system once more, with Jupiter forming first from the rich outer disk. As it plowed through the thick gas, it began the expected inward migration, a slow spiral toward the sun. This journey was not gentle. A migrating Jupiter is a gravitational bulldozer, and it would have pushed and swept a vast amount of primordial material ahead of it, clearing a wide path. For a time, it looked as though the solar system's largest world was on a collision course with the inner planets, threatening to plunge into the sun itself and utterly disrupt the formation of Earth and its siblings. But then, something extraordinary happened. Saturn, forming a bit later and farther out, began its own inward migration. It began to catch up. When Saturn finally entered a specific orbital resonance with Jupiter, their gravitational relationship changed the game entirely. This resonance, a different lockstep than the one that triggered the later chaos, acted like a cosmic leash. The combined gravitational pull of the two giants on the gas disk created a powerful braking effect. Jupiter's inward march halted, and then, under Saturn's persistent tug, it reversed. Like a massive sailboat tacking against the wind, Jupiter changed direction. It began to migrate back outward, away from the sun, with Saturn following close behind. This grand tack, this breathtaking reversal, solves multiple puzzles in one stroke. First, it explains why Jupiter did not continue its deadly plunge into the inner solar system and destroy everything in its path. Second, and more crucially, it explains the small size of Mars and the very existence of the asteroid belt. As Jupiter first moved inward, its gravity would have shepherded and swept most of the solid material from the region where Mars was forming, stealing the red planet's building blocks and leaving it stunted. Then, on its outward tack, Jupiter would have herded some of the remaining debris back into a narrow band, effectively constructing the asteroid belt we see today from the scattered leftovers. This belt is not a failed planet, but a construction zone that was emptied and then partially refilled by a passing giant. The Grand Tack hypothesis paints Jupiter not as a passive wanderer, but as an active, dynamic sculptor whose two-part journey may have been the single most important event in determining the architecture of our entire inner solar system. Yet this grand cosmic dance required a partner. While Jupiter often takes center stage as the solar system's gravitational heavyweight, it could not have performed this intricate maneuver alone. The true architect of our system's stability may not be the king, but its majestic sibling, Saturn. Without Saturn's steadying influence, Jupiter's migration would have been a story of pure destruction, a runaway train with no brakes. Jupiter's immense mass gives it a gravitational pull that can fling worlds into the void or send them spiraling into the sun. Left unchecked during its early inward spiral, It could have ejected Uranus and Neptune entirely, or plunged so deep into the inner system that it would have scattered the rocky planets like billiard balls. The solar system we know would not exist. Saturn changed everything. Think of it not as a passive follower, but as the responsible older sibling, the one who reigns in the powerful but impulsive younger one. As Jupiter began its inward migration, Saturn, forming farther out, eventually felt the pull and began its own journey sunward. When Saturn finally caught up and locked into a resonant orbit with Jupiter, their gravitational relationship transformed from independent motion into a coupled system. This resonance created a feedback loop. Saturn's gravity acted as a brake on Jupiter's inward rush, and Jupiter's gravity, in turn, guided Saturn's path. They became a single gravitational unit, moving in concert. This partnership is what made the Grand Tack possible. The combined gravitational tugs of the two giants on the protoplanetary disk created a barrier, a shared zone of influence that halted their inward progress and eventually pushed them back outward together. Saturn provided the counterweight, the stability that allowed for a controlled reversal instead of a chaotic crash. Even later, during the violent reshuffling of the NICE model, Saturn's role was again crucial. Its specific 2-to-1 resonance with Jupiter was the trigger, yes, but it also helped dictate the outcome. The precise way their orbits interacted set the rules for the gravitational pinball game that followed, ensuring that while the system was violently rearranged, it was not utterly obliterated. Planets were scattered, but not all were lost. Orbits were changed, but a new, lasting order eventually emerged. Saturn's gravity was the guide rail that kept the chaos from tipping into total annihilation. So when you look up at the ringed planet, remember it is more than a beautiful spectacle. It is the solar system's great stabilizer, the gravitational moderator whose presence meant the difference between a habitable system with an Earth in the right place and a cosmic junkyard of ejected worlds and shattered dreams. The journey of the ice giants is a story of cosmic billiards on the grandest scale. Uranus and Neptune were not passive observers of the solar system's reshuffling. They were its primary projectiles, flung through the primordial construction zone with world-shattering force. Their current positions are almost certainly swapped from their original birth order. In the early compact configuration, Neptune likely formed closer to the Sun than Uranus. But when the resonant lock between Jupiter and Saturn triggered the chaos, the resulting gravitational shove sent both ice giants careening outward. In the ensuing scramble, Neptune, perhaps receiving a more forceful series of kicks, was catapulted past its sibling, claiming the outermost orbit we see today. This swap is not just a curious detail, it is a predicted outcome of the gravitational models that recreate the migration, a signature of the violence that occurred. Their outward migration was anything but a smooth cruise into open space. They plowed directly into the dense disk of icy planetesimals, the leftover building blocks beyond the giants. Each close encounter with these frozen worlds was a gravitational transaction. The ice giant's immense gravity would hurl the smaller body onto a wild new path, sending it sunward to become a comet or ejecting it entirely from the solar system. But for every action, there is an equal and opposite reaction. Each time Neptune scattered an icy planetesimal away, it experienced a tiny recoil, a minuscule push that added up over thousands upon thousands of encounters. This process, gravitational scattering, acted as a relentless engine, slowly but surely driving the ice giants farther and farther from the Sun until they reached their present lonely distances. This epic journey also explains their profound oddities. Take Uranus spinning completely on its side. Its rotation axis is tilted a staggering 98 degrees, so it essentially rolls around the Sun like a cosmic bowling ball. Such an extreme tilt is almost certainly the result of a colossal impact during this chaotic migration phase. A single, glancing blow from an Earth-sized protoplanet, or perhaps a series of massive collisions, could have knocked the entire world over, leaving it with its peculiar, sideways spin for eternity. Neptune, too, bears the marks of this violent past in its captured entourage. Both ice giants are surrounded by families of irregular moons, small, rocky objects in distant, tilted, and often backward orbits. These are not moons that formed alongside their planets from a neat disk of gas. They are prisoners of war, captured asteroids and planetesimals that wandered too close during the giants' furious migration and were gravitationally shackled into orbit. Their chaotic paths are frozen records of the traffic that once filled the outer solar system. So when we look at Uranus and Neptune today, we are not seeing serene, quiet giants. We are seeing the survivors of a gravitational storm, their final positions, their tilted spins, and their captured moons all serving as permanent testimony to the day the solar system tore itself apart and rebuilt its outer frontier. This violent scattering created a new frontier, a frozen graveyard of survivors now known as the Kuiper Belt. Far beyond the orbit of Neptune, stretching billions of miles into the dark, lies a vast, diffused disk of icy worlds. This is not the serene, primordial ring of debris you might imagine. The Kuiper Belt is a refugee camp, a celestial archive populated by the lucky escapees of that ancient gravitational storm. These frozen bodies, including dwarf planets like Pluto, are the ones that were not flung into the sun, not ejected into interstellar space, and not captured by the giant planets. They are the remnants that managed to find a precarious stability in the distant outskirts after the chaos subsided. Their very existence and the specific patterns of their orbits are direct fingerprints of the Great Migration. If Neptune had always been in its current quiet orbit, the Kuiper Belt would look entirely different. It would be a smooth, dense, and circular reservoir of primordial ice. Instead, what we see is a sharply sculpted and surprisingly empty region. Neptune's grand outward march acted like a cosmic plow, clearing out most of the material from its path. The objects that remain are clustered into distinct families with peculiar, elongated orbits. Many, like Pluto, are locked in a gravitational dance with Neptune, completing 2 orbits for every 3 of the giant planet. This orbital resonance is a telltale sign of capture. It means these objects were gently shepherded into their current paths by Neptune's migrating gravity, like a series of gears clicking into place as the planet moved outward. The Kuiper Belt, therefore, is not a leftover construction zone. It is a carefully arranged museum of the solar system's violent youth, its icy inhabitants forever telling the story of the day the giants went to war and reshaped the cosmos. The structure of this distant belt is anything but random. It reveals a sharp, almost artificial-looking outer edge, as if someone drew a line in the cosmic sand and said, "Nothing beyond this point." This is not how a primordial disk of debris should naturally end. It is a boundary carved by history. Within the belt itself, the icy inhabitants fall into 2 distinct families with dramatically different personalities, known as the cold classicals and the hot scattered disk objects. The cold classicals are the quiet survivors. They orbit in near-perfect circles close to the plane of the solar system, like well-behaved children staying in their lanes. These objects are thought to be the true, pristine relics of the original outer disk, the ones that were barely disturbed during the chaos. They survived by sheer luck, orbiting in a region that Neptune's gravitational influence never quite reached during its migration. Their circular, flat orbits are a frozen snapshot of the calm that existed before the storm. Then there are the hot ones. The scattered disk objects are the wild refugees. Their orbits are highly elongated, tilted, and eccentric, taking them on extreme journeys that swing far from the sun before diving back in. These are the escapees, the ones that felt the full force of the migrating giants. They were gravitationally scattered by Neptune, flung onto these wild, looping paths, but were just barely retained by the sun's gravity, forever marking the outer frontier of its influence. This stark division between cold and hot populations is a direct prediction of the migration models. Neptune's outward journey acted like a great cosmic sieve. As it moved, its gravity captured and corralled the quieter objects into resonant orbits or left the cold classicals undisturbed in a narrow lane. Meanwhile, it violently tossed other bodies into the scattered disk, creating a halo of chaotic orbits. Pluto is the most famous member of this dynamical story. It is not a cold classical. Its orbit is tilted and eccentric, and it is locked in a stable resonance with Neptune, completing 2 orbits for every 3 of the giants. This is no accident. Pluto did not form in this peculiar dance. It was captured into it. As Neptune migrated outward, its shifting gravitational influence swept up objects like Pluto, herding them into these resonant orbits like a shepherd guiding sheep into a pen. Pluto's very existence in its current orbit is a fossilized record of Neptune's grand migration. So the Kuiper Belt is not a simple ring of ice. It is a dynamically sorted archive, its sharp edges and divided populations serving as permanent, observable proof that the giant planets once roamed, sculpting the solar system's final frontier with their gravity. Beyond this sculpted belt lies a deeper darkness and a more profound mystery. The gravitational reach of our Sun extends much farther than the Kuiper Belt, into a vast spherical shell of icy bodies known as the Oort cloud. This is the solar system's final frontier, a place so distant and faint its inhabitants are almost impossible to see. Yet a few have been found, and they tell a story that challenges everything we think we know. These are the extreme trans-Neptunian objects, and their king is a world called Sedna. Discovered in 2003, Sedna follows an orbit of breathtaking loneliness. At its closest approach, it is still far beyond Pluto. Then it embarks on an unimaginable journey, swinging out to a distance over 900 times farther from the Sun than Earth. Its entire, wildly elongated orbit is contained within this deep freeze. It never comes close enough to any of the known giant planets for their gravity to have shaped its path. This is the core of the mystery. How did Sedna get there? An orbit like this does not form by accident in a calm, orderly system. It is a scar, a trajectory that screams of a violent gravitational encounter in the distant past. Something massive must have perturbed Sedna, flinging it onto this isolated, looping path, and then retreated, leaving no trace. The giant planets, busy with their own migration, could not have done this alone. Their gravity simply does not reach far enough to explain Sedna's exile. This forces astronomers to consider 2 extraordinary possibilities, each pointing to a dramatic event during the solar system's infancy. The first is a stellar close encounter. Our Sun was not born in isolation. It formed within a dense cluster of sibling stars, a stellar nursery where close passes would have been common. A wandering star from this cluster, passing relatively near our young solar system, could have reached out with its gravity. It would have stirred the outermost debris, plucking objects like Sedna from the primordial disk and tossing them onto these detached, far-flung orbits before moving on into the galactic night. The second possibility is even more tantalizing. Perhaps the perturbing force never left. Could there be an undiscovered planet, a true giant, still lurking in the perpetual twilight far beyond Neptune? This hypothetical world, often called Planet 9, would be massive enough to shepherd not just Sedna, but a whole population of extreme objects into similar, tilted orbits. Its distant gravitational influence would be the unseen hand organizing these distant icy bodies, a ghost from the migration era that never fully joined the inner family. Sedna is therefore more than a curious frozen world. It is a clue, a celestial detective pointing to forces that acted upon our solar system from the outside or from the deepest shadows within. Its impossible orbit suggests our story is incomplete, that the Great Migration may have involved characters we have yet to meet, their influence frozen in the slow dance of ice at the edge of everything. Sedna's lonely path is not the only one of its kind. It is part of a pattern, a cluster of extreme icy objects all pointing in the same general direction, their elongated orbits tilted in a similar way. This strange alignment is statistically improbable, a cosmic wink suggesting something unseen is herding them. To explain this, astronomers have revived a thrilling possibility, the Planet 9 hypothesis. This is the idea that a true giant, a world perhaps 5 to 10 times the mass of Earth, still hides in the perpetual gloom of the outer solar system. Its distant gravitational hand would be the organizing force, the shepherd guiding these detached orbits into their peculiar family portrait. But where could such a planet come from, and how could we have missed it? The answer may be buried in the very migration story we have been telling. One compelling origin story casts Planet 9 not as an intruder but as a refugee. During the violent reshuffling of the NICE model, as Jupiter and Saturn flung Uranus and Neptune outward, the gravitational chaos would have been extreme. It is entirely possible that a fifth giant planet, a sibling to these ice giants, once orbited among them. In the pinball game of that era, this world could have received a particularly fierce gravitational kick, not inward, not into a stable outer orbit, but onto a wildly elliptical path that takes it hundreds of times farther from the Sun than Neptune. It would have been ejected, but not entirely. The Sun's gravity, weakened at such a distance but still present, could have captured it on this monstrous million-year-long orbit, forever tying it to our system as a ghostly, distant member. This would make Planet 9 a fossil, a primordial giant that witnessed the solar system's violent birth and was cast into the deep freeze as a result. An alternative, equally dramatic origin imagines it as a cosmic orphan. In the Sun's crowded stellar nursery, close encounters with other newborn stars were common. The gravity of a passing star could have stripped a giant planet from its own system and flung it toward ours where our Sun's gravity captured it. Or perhaps our Sun's gravity could have directly stolen a world from a weaker sibling star's outer disk. In this scenario, Planet 9 would be an interstellar immigrant, a captured wanderer that found a new home in the furthest reaches of our system during that chaotic early era. Both stories tie back to migration, either the internal migration of our own giants or the grand migration of stars within their birth cluster. Finding this world, if it exists, would be the ultimate validation of our chaotic history. It would confirm that the Great Migration did not just rearrange the furniture. It may have left a hidden giant in the attic, a permanent reminder of the gravitational storms that built our home. The search for other worlds has revealed our solar system is not the blueprint. For decades, we assumed all planetary systems would look like our own, with small rocky worlds close to the star and gas giants orbiting peacefully in the cold outer reaches. The discovery of exoplanets shattered that assumption, and in doing so, handed us the most powerful evidence that planetary migration is not just our history, it is the universe's rule. The most shocking and definitive proof came in the form of worlds called hot Jupiters. These are gas giants like Jupiter, but they orbit blisteringly close to their parent stars, completing a full revolution in just days or even hours. Their surfaces, if they have a surface, would be scorched by stellar radiation, a place of unimaginable heat and violence. According to traditional formation theories, these monsters simply cannot exist where we find them. A gas giant cannot form that close to a star. The environment is too hot and the disk of material too thin to build such a massive world. There is only one explanation. Hot Jupiters must have formed much farther out, in the cooler, richer regions of their protoplanetary disks, and then migrated inward dramatically to their present infernal orbits. They are the ultimate migrants, worlds that have completed the terrifying journey our own Jupiter only began, a journey that in other systems did not have a Saturn to pull them back. This discovery was a revolution. It proved migration is not a rare catastrophe. It is a standard, perhaps inevitable, phase of planetary system evolution. Our solar system is not special in experiencing a great migration. We are special in how it ended. The chaotic reshuffling we went through appears to be a common growing pain for young stars and their families of planets. What makes our home unique is the surprisingly gentle outcome for the inner rocky worlds, Earth in particular. In many other systems, the inward march of giant planets does not stop, it does not reverse. It continues until those giants either plunge into their star or settle into a searingly close orbit, wiping out or ejecting any smaller planets in their path. Our system had a different story, a story of gravitational teamwork and fortunate timing. Jupiter's grand tack, its outward reversal, and the eventual resonant lock that triggered the late heavy bombardment were violent, yes, but they were also precise. They cleared the inner system just enough to allow Earth to form and retain its water, but not so much as to sterilize it completely. We live in the product of a controlled demolition, not a total collapse. The Great Migration is everywhere we look in the galaxy, but the peaceful, habitable order it left behind here may be the universe's rarest gift. Yet this elegant story is not the final word. The nice model, for all its explanatory power, faces serious challenges under the relentless scrutiny of modern supercomputers. When scientists attempt to reenact the Great Migration in digital simulations, they often find the process is far too violent for comfort. In many of these virtual reruns, the gravitational pinball game does not just rearrange the outer planets, it annihilates the inner ones. The chaotic dance of the giants sends shockwaves so severe that Mercury, Venus, Earth, and Mars are frequently ejected into space or sent crashing into the Sun. Our existence in these models becomes a statistical miracle bordering on impossible. This is a profound problem. If the most likely outcome of a planetary migration like ours is the destruction of the terrestrial worlds, then why are we here? It forces a difficult question. Are we simply the beneficiaries of incredibly good luck, or is our understanding of the early solar system's conditions still incomplete? Perhaps the protoplanetary disk was smoother, or the planet's initial orbits were more carefully spaced, providing a stability that our current simulations have yet to capture. This tension between model and reality is where real science happens, a constant push and pull between a beautiful story and the unforgiving math of gravity. A second, more subtle complication is the question of timing. The original NICE model elegantly linked the planetary instability to the late heavy bombardment, that spike in lunar impacts around 3.9 billion years ago. But newer, higher-resolution simulations sometimes tell a different story. They suggest the giant planet instability may have happened much earlier, perhaps only a few 100 million years after the planets formed. If that is true, then the cataclysmic rain of impacts on the Moon cannot be a direct, immediate consequence of the migration. The clockwork falls out of sync. This forces astronomers to consider alternative triggers for the late heavy bombardment, or to refine the model so the bombardment is a delayed effect, like boulders taking centuries to fall after an earthquake. Perhaps the instability did happen early, but it took hundreds of millions of years for the scattered debris to finally rain down on the inner planets. Or maybe the bombardment had a different source entirely, a later, quieter event we have yet to identify. These are not failures of the theory, but signs of its maturity. A good scientific model must withstand new data and more powerful tests. The debates over violence and timing are not tearing the story down, they are refining it, carving away the parts that do not fit until a clearer, more robust history emerges from the stone. The search for a less violent past has given rise to new models, each trying to solve the puzzle of our survival. One prominent alternative is the 5-planet model. It starts with a simple, elegant premise. Our solar system originally had not 4 but 5 giant planets. This extra ice giant, a sibling to Uranus and Neptune, orbited between Saturn and the original Uranus. In this scenario, the Great Migration still happens, triggered by the same resonant instabilities. But when the gravitational pinball game begins, the system has a sacrificial piece. The chaotic interactions do not need to threaten the rocky inner worlds as severely because they have another giant to absorb the violence. In the models, this fifth giant is not gently nudged. It is brutally ejected. A close encounter with Jupiter acts as a gravitational slingshot, hurling this entire world out of the solar system at tremendous speed, sending it on a one-way trip into interstellar darkness. Its departure acts as a pressure valve, releasing enough gravitational energy to allow the remaining four giants to settle into their current orbits without causing total carnage in the inner system. It is a dramatic idea that a lost sibling planet was the price paid for our stable existence. We may be living in a solar system that sacrificed one of its giants to save the rest. This model elegantly explains the extreme orbits of some distant icy bodies and makes our survival less of a miraculous fluke. It suggests the violence was focused on the outer solar system, with one world taking the fatal hit so that Earth could live. Other theorists propose a completely different pace for the entire drama. What if the migration was not a sudden, catastrophic event at all, but a slow, gentle, and continuous process? In these models, there is no single instability, no resonant bomb waiting to go off. Instead, the giant planets migrated smoothly and gradually over hundreds of millions of years, driven by gentle interactions with the leftover planetesimals. Their orbits slowly expanded, like ink diffusing in water, pushing and sculpting the debris disk as they went. This peaceful migration could still deliver comets to the inner solar system to cause a bombardment, but it would be a steady drizzle over eons, not a sudden, cataclysmic storm. The challenge for this idea is the Moon itself. Its surface tells a story of a sharp spike in violence, not a long, gentle rain of impacts. So perhaps the truth is a hybrid, a slow migration punctuated by a final, sharper instability. These competing ideas are not failures, they are the sound of science at work. The classic NICE model gave us the foundational story, but like any good mystery, the details are being refined with every new discovery and every more powerful simulation. The story of the Great Migration is not a settled chapter in a textbook. It is a living narrative, constantly rewritten by the clues we find in the orbits of distant ice, the scars on our moon, and the silent testimony of planets that may have once been here and are now gone forever. These digital time machines are our only window into that vanished era. To understand the ancient chaos, astrophysicists build entire solar systems inside supercomputers using a powerful tool called an N-body simulation. The N simply stands for the number of objects in the dance. It could be 4 planets or 400,000 icy planetesimals, or millions of individual particles of gas and dust. The computer's task is brutally simple yet computationally immense. It must calculate, moment by virtual moment, how every single one of these objects gravitationally tugs on every other one. It tracks their positions, their velocities, and the invisible forces between them, projecting their motions forward across billions of years of simulated time. This is not a simple animation. It is a physics experiment run in a universe of pure mathematics where gravity is the only law. The goal is to rewind our current solar system and hit play, testing different starting conditions to see which ones, through the unfeeling logic of gravitational physics, evolve into something that looks like the cosmic home we see outside our window. Scientists begin with a hypothesis, a possible starting configuration for the infant planets. Perhaps the giants were tightly packed, perhaps there was a fifth world. They feed this initial setup into the simulation, along with a vast sea of virtual planetesimals. Then they press start and the digital cosmos comes to life. On screen, points of light begin to move, orbits stretch and warp, close encounters fling worlds onto wild new paths. Some simulations end in peaceful, orderly systems that look nothing like our own, proving that hypothesis wrong. Others erupt into spectacular violence, ejecting planets into the void or sending them crashing into the sun. The researchers are looking for that rare, beautiful middle path, the simulation where the chaos is just right. Where Jupiter tacks, where Neptune migrates outward and captures Pluto, where the asteroid belt is cleared but not destroyed, and where, at the end of billions of virtual years, the digital planets settle into orbits that match with stunning precision the exact spacings and tilts we observe today. Each successful run is a story that works, a possible history for our solar system written in the language of gravity and confirmed by silicon. But these simulations are more than just cosmic reruns. They allow for terrifying experiments we could never run in reality. What if Jupiter had been slightly more massive? The simulation shows it devouring the inner solar system. What if the primordial disk had been smoother? The migration might never have triggered at all. By tweaking these initial conditions, we learn not just what did happen, but what could have happened. We see how perilously close our existence came to never being, and we gain a profound appreciation for the fragile chain of gravitational events that led, against staggering odds, to the stable platform beneath our feet. The story of the Great Migration is written in the sky, but to read its finest print, we must go there. Our next chapter will not be written by telescopes or simulations alone, but by spacecraft venturing into the deep, hunting for the primordial witnesses to that ancient chaos. A new generation of robotic explorers is preparing for journeys that are, in essence, time travel missions. They are going to find the scattered survivors and ask them directly where they came from. Leading this charge is NASA's Lucy mission, a spacecraft already on its way to a destination unlike any other. Lucy is not heading to a planet but to Jupiter's Trojan asteroids. These are two vast swarms of ancient rocks, one leading and one trailing Jupiter in its orbit around the Sun, trapped in gravitational parking spots known as Lagrange points. For decades, their origin was a mystery. Are they asteroids from the inner belt that wandered out, or are they something far more primitive? The leading theory, strongly supported by the migration models, is that the Trojans are captured refugees. They are pristine planetesimals from the outer solar system, the very building blocks of the giant planets that were swept up and captured by Jupiter's gravity during its grand migration. Lucy will fly by multiple of these Trojan asteroids, giving us our first close-up look at these cosmic fossils. By analyzing their composition, density, and structure, Lucy can test this origin story. If they are rich in water ice and organic compounds, resembling the comets of the Kuiper Belt more than the rocky asteroids of the inner system, it will be powerful, direct evidence that Jupiter's journey did indeed herd primordial outer solar system material into its orbit. This would be a tangible piece of the migration puzzle, a captured relic from the era of wandering giants, but our ambition stretches even farther. Concepts are being drawn for a mission called the Interstellar Probe, a spacecraft designed to travel far beyond the heliosphere, the bubble of our Sun's influence. One of its potential paths would take it speeding through the Kuiper Belt and into the scattered disk, the realm of the hot, wild refugees. Flying by one of these extreme objects, a sibling to Sedna, could provide a revolutionary dataset. Measuring its composition and imaging its surface would tell us if it truly is a primordial object flung outward, and its exact orbit would provide a critical data point for testing the Planet 9 hypothesis. The ultimate prize, however, lies in the dream of sample return. Imagine a spacecraft traveling to a distant Trojan asteroid or a Kuiper Belt object like Arakoth, that strange, bilobed snowman we flew past, and bringing a piece of it back to Earth. In our laboratories, we could perform forensic chemistry on a scale no spacecraft instrument ever could. We could search for isotopic fingerprints, the unique atomic signatures locked into the rock and ice. The ratios of different isotopes of oxygen, nitrogen, or noble gases act as a cosmic barcode, telling us precisely where in the primordial solar disk that object formed. A sample from a Trojan that carries the isotopic signature of the outer solar system would be the smoking gun, definitive proof that it was captured during the migration. Each of these missions is a detective sent to interrogate a silent witness. They seek to transform our elegant theoretical story, written in gravity and simulations, into a history written in rock and ice. The data they send back will either confirm the epic tale of wandering planets or force us to write a new, even more astonishing one. This cosmic history is not a remote event, it is the story of our own existence. The Great Migration did more than rearrange planets, it set the stage for life itself. Consider the delicate balance Earth enjoys. We orbit within a narrow band of space where liquid water can persist, the so-called habitable zone. But a warm orbit alone is not enough. A world also needs stability over billions of years and, crucially, the right ingredients. Jupiter's journey may have been the key to both. Its role as a gravitational shield is legendary. After its migration settled, Jupiter's immense mass began acting as a cosmic vacuum cleaner, its gravity deflecting or capturing countless comets and asteroids that might otherwise have crossed Earth's path. This protective influence is thought to have drastically reduced the rate of catastrophic impacts, allowing life the long periods of calm it needed to emerge and evolve. Without that distant giant standing guard, our planet might have been subjected to a relentless, sterilizing bombardment, a fate that could have befallen many promising worlds in other systems. Yet the same migration that provided later protection also delivered the very essence of life. The late heavy bombardment, that violent rain triggered by the planetary instability, was likely a double-edged sword. While it scarred the moon and battered the young Earth, it also carried precious cargo. Many of those impacting bodies were not dry rocks, but water-rich planetesimals and comets, icy remnants from the outer solar system that were hurled inward by the migrating giants. They may have been the couriers that delivered Earth's oceans, along with complex organic molecules, the building blocks of biology. In this light, the migration was not merely destructive, it was a delivery system. It took the volatile materials, the water and carbon compounds, that formed in the cold outer disk and transported them to the warm, rocky world where they could become the soup of life. Our blue planet, teeming with life, might be a direct product of that ancient gravitational storm. This forces a profound question about our place in the universe. Is our solar system's turbulent history a universal recipe for habitable worlds, or are we the beneficiaries of a series of incredibly fortunate accidents? The discovery of hot Jupiters in other systems shows that violent migration is common, but often with apocalyptic results for small inner planets. Our system seems to have threaded a needle. Jupiter migrated, but its inward spiral was halted and reversed by Saturn. The instability happened, but it was not so severe as to eject Earth. The bombardment occurred, but it was intense enough to deliver water, yet not so relentless as to boil the oceans away. Each step was a precarious balance. If any variable had been slightly different, the giant planet's gravitational pinball game could have left our orbit empty, or our world a dry, barren rock. This suggests that quiet, stable solar systems like ours, with a habitable planet in the right place for billions of years, may be exceptionally rare jewels in the cosmos. Our existence is not just a product of chemistry and light, but of celestial dynamics, of a gravitational dance performed with just the right steps, at just the right time, leaving behind a world perfectly poised for life to take hold. The stability we enjoy today is a temporary gift, a snapshot in a story that is far from finished. Our solar system's great migration may have settled into a quiet rhythm, but the clock is still ticking. The gravitational dance of the planets is a slow, relentless force, and over timescales that dwarf human history, their orbits remain in a state of delicate, chaotic evolution. This is not the violent pinball game of the past, but a subtle, persistent drift driven by the same fundamental rules. The planets continue to tug on one another, their influences resonating in tiny, cumulative ways that can, over billions of years, lead to significant changes. Computer models that project the solar system's future reveal a surprising truth: complete long-term predictability is impossible. The interactions are so complex, the system so sensitively balanced, that we cannot say with certainty where each planet will be in a billion years. There is a chance, however small, that Mercury's orbit could become so elongated it eventually crosses paths with Venus, triggering a new cascade of instability. Our current order is stable, but it is not eternal. It is a chapter in a book still being written by gravity itself. The greatest change, however, will come not from the planets but from the heart of the system. In about 5 billion years, our Sun will exhaust the hydrogen fuel in its core and begin its transformation into a red giant. This is not a distant abstraction, it is the inevitable fate of our star. As it dies, the Sun will swell to a monstrous size, its outer layers expanding to engulf the orbits of Mercury and Venus, and likely reaching out to Earth itself. Our world, if it still exists, will be swallowed by a sea of plasma, its rocks and oceans vaporized in an instant. But even in this apocalyptic finale, the story of migration continues. As the Sun loses mass during its giant phase, its gravitational grip on the surviving planets will weaken. Their orbits will expand in response, drifting outward into the growing void. Mars, the asteroids, and the giant planets will all shift, moving farther from the dying ember of their star. It is a final, slow retreat, a cosmic recession driven by stellar death. What remains after the Sun's final breaths is perhaps the most poignant migration of all. After the red giant phase, our Sun will shed its outer layers, leaving behind a dense, Earth-sized core called a white dwarf, a fading diamond of carbon and oxygen that will glow with residual heat for trillions of years. In this new, stark system, the surviving planets Jupiter, Saturn, the ice giants will orbit a ghost of their former sun. Their expanded orbits may be stable for eons, but they will not be untouched. The gravitational interactions between them will continue their slow work. Over unimaginable timescales, these subtle tugs could still perturb orbits, potentially ejecting a world into interstellar space or sending it spiraling inward toward the white dwarf. Astronomers have even observed evidence of such late-stage chaos around other white dwarfs, finding the chemical signatures of pulverized planets in their atmospheres, the final remnants of alien solar systems that migrated and collided long after their stars died. So when we look up at the night sky and see the familiar planets tracing their predictable paths, we are witnessing a moment of profound but fleeting peace. The Great Migration never truly ended, it merely changed pace. From the violent reshuffling of infancy to the subtle chaotic drift of today, to the grand orbital expansion during the Sun's death, our solar system is in a constant state of gravitational becoming. The orbits we map so precisely are not destinations, they are waypoints in an endless journey. This perspective transforms our home from a static clockwork into a living, breathing entity with a deep past and an uncertain future. We are living in the calm eye of a storm that took billions of years to form, and will take billions more to fully dissipate, temporary residence on a world whose very position in space is the gift of ancient wanderers. From that compact, crowded nursery of infant worlds to the spacious, stable system we now call home, the journey has been nothing short of epic. The quiet orbits we see today are a beautiful lie, a peaceful facade over a past of unimaginable violence. Our planets are not fixed monuments in the sky. They are travelers, each bearing the scars and stories of a great migration that reshaped everything. Jupiter's inward tack and outward retreat, Saturn's steadying hand, the ice giants flung like billiards through a sea of ice, the rain of comets that scarred the moon and filled our oceans, these are not separate events. They are chapters in a single, grand narrative of gravitational chaos and hard-won order. This story transforms our cosmic neighborhood from a static museum into a dynamic, living entity with a deep and turbulent history. We are not living in a perfect, preordained clockwork. We are living in the aftermath of a storm, on a planet whose very existence and habitability hinge on a series of precarious, fortunate events that unfolded billions of years ago. That connection is profound. It means the night sky is not just a display of distant lights, but a map of an ancient journey, a testament to resilience written in orbital paths and captured moons. It connects our small, blue world directly to the most fundamental forces of the universe, reminding us that we are part of a dynamic, ever-changing cosmos, not merely observers of it. So the next time you look up, remember the Great Migration. See the planets for what they truly are, survivors, travelers, and sculptors of our shared history. Which part of this epic story stays with you the most? Is it the haunting mystery of a possible Planet 9, still lurking in the dark, the stunted fate of Mars, forever small because of a passing giant, or the sheer violence of the late heavy bombardment that may have delivered the water in your glass? Share which cosmic mystery intrigues you most as we continue to piece together the story of our wandering